Thank you very much, Lorenzo, for the introduction. And thank you, the organizers, for the invitation. It's my great pleasure to speak here. And so the notes I have put in the chat, and you are welcome to read back and forth during my talk. And also, please do not hesitate to ask questions and interrupt me. So the title of my talk is Generalizing GKZ Secondary Fan Using Berkovich Geometry. It is in my joint work, part of my joint work with Paul Hacking and Keel. Actually, I have been talking about this joint work from different viewpoints, but I never really emphasized on this generalization of the GKZ secondary fan because it uses some non-Archimedean geometry, and usually in conferences, people are not that familiar with non-Archimedean geometry. But I think now this is a great occasion for me to talk more details about this secondary fan story. Here is the plan of my talk. I will begin by reviewing what is a GKZ secondary fan. It's a classical subject introduced by Gelfand-Kapranov-Zelevinski in their famous book. It's actually very elementary construction. If you didn't know it before, you will see it's very easy. Actually, I also, before working on this project, I also only know the name of the object. And then I will explain our generalization of the GKZ secondary fan. And after that, I will explain what were our motivations. So our motivations came from moduli space, the study of the moduli space of Calabial pairs. And finally, I will explain like why we really study this secondary fan is because we will have a very nice family of varieties. So we will get so-called very nice family of KSBA stable pairs over this secondary fan. And this notion of stable pairs is the correct generalization of nodal curves into higher dimensions. So it's really for compactification of moduli space of varieties. Okay, let me start with the elementary part, most elementary part, this combinatorial construction. Yeah, so it's purely combinatorics. We have some lattice polytope Q, and we are interested in triangulations of Q with vertices in the integer lattice points inside Q. So this is what we consider. And a triangulation T of Q. So you know what I mean. We have polytope, some lattice points, a lattice polytope and some lattice points inside. Then we want to triangulate the polytope. So we only consider triangulations where the vertices or this zero-dimensional, these points of the triangulation are these lattice points. A triangulation is called coherent if there exists a concave T piecewise linear function whose domain of linearity are precisely the maximal simplices of T. So when we have such piecewise linear function with respect to the triangulation, and if the piecewise linear function has domain of linearity exactly the triangulation, then this is a nice one. We call it coherent. when we have T triangulation of Q and psi from A to R, any function, A is the lattice points in Q. And then we have a unique, so any such function determines a unique T piecewise linear function which coincides with psi over the vertices of T. So it's obvious because to get such a T piecewise linear function, we only need to specify the values of the function at the vertices of the triangulation. So it determines uniquely such a function. Now, whenever we have a triangulation, we let Ct be the cone in R to the power A, consisting of functions psi from A to R, such that first of all, we get a concave function. The associated G psi T is a concave function. And the second, we want this G is to be greater or equal to psi. So for each triangulation, we get a cone inside this space of functions, which is just Euclidean space. I hope it's very elementary and clear. Now we observe that the definition of coherent is simply equivalent to the statement that the cone has non-empty interior. Okay, so that's all we need for defining this GKZ secondary fan. It's proved in the book by GKZ that the cones CT for all the coherent triangulations of Q together with all faces of these cones form a complete fan in R to the power A. And this complete fan is called GKZ secondary fan, Gelfand-Kapranov-Zelevinski secondary fan. So that's all what it is. And let me give some remarks. First, this GKZ secondary fan is the normal fan of some polytope called the secondary polytope. So in the book, first they introduced the secondary fan, and then later they also introduced the secondary polytope and showed that the secondary fan comes from the secondary polytope as the normal fan. It is used by GKZ in the study of the Newton polytopes of discriminants and the resultants. This is the main theme of their book. And furthermore, this secondary fan controls the geometric invariant theory for toric varieties. Okay, so this is all I want to say for the elementary picture of the secondary fan. If you have any questions, please do not hesitate. Okay, maybe let me try to close my door so that I don't interrupt. I don't. Okay, yes. And now let me introduce a generalization of the above combinatorial picture. So our idea is that although before it's just a combinatorics, but one can also phrase it in terms of toric varieties, and that's why it's related to the GIT theory for toric varieties. Now we would like to propose a generalization of this combinatorial construction into varieties, into Fano varieties that are not necessarily toric. Here is our setup. We have V any smooth log Calabial, and K of V a smooth partial compactification. Hello? Yes, please. Thank you. Yeah, we have V smooth log Calabial, and K partial compactification of V. And furthermore, we fix a regular proper map Q from K to K bar. And we assume that this map Q is a relative Mori dream space. I will explain it in a moment. So yeah, it's maybe complicated, a little bit complicated notations, but we don't have many things. Just VK and K to K bar. We have three symbols here. In our application, we have YD Fano. In our application, we will apply this to a pair YD, where Y is Fano and D is some normal crossing divisor. U is the interior, and we take a canonical bundle K over Y, and this V here will be the restriction of the canonical bundle over this interior U, and the K and this Q from K to K bar will be contraction of the zero section of this canonical bundle. So I will explain this again when we actually apply to the case of Fano. Maybe now for the moment, you can just keep in mind this more general setup. It's just Calabial partial compactification together with some contraction map. Yeah, so we have V Calabial, some partial compactification K, and we contract something in K. We get K bar. Let me explain what is Mori dream space. So the idea is that a Mori dream space is a projective variety such that the Mori equivalence of line bundles gives rise to a finite polyhedral fan called the Mori fan. I will recall right away what are Mori equivalence relations of line bundles. So when we have this equivalence relation, we get a partition of the effective cone inside the Picard vector space. And in general, it's just very complicated, this partition. But the Mori dream space is a projective variety where such a partition or such an equivalence gives rise to something polyhedral, gives rise to a finite polyhedral fan. And this is what Mori dream space is. And this finite polyhedral fan is called Mori fan, which we denote by this Mori fan of X. So what's really nice about getting this finite polyhedral fan out of Mori equivalence is that Mori's minimal model program becomes particularly simple for this kind of spaces. One can actually see explicitly what it means, like what are the flops of the minimal model program. One can write it totally explicitly when this condition is satisfied. Now let me just recall what is Mori equivalence. So it's some equivalence relation between line bundles. When we have any line bundle L on the projective variety X, we can consider its a section ring R XL, which is just a direct sum of all sections of powers of the line bundle L. And yeah, so in the case where this section ring is finitely generated, we obtain a birational contraction from the projective variety X to the proj of this section ring. Now, two Q line bundles with finitely generated section rings are called Mori equivalent if they give rise to first the same birational contractions here. And furthermore, we ask them to have the same stable base divisors. So if there are no base divisors, we only ask that they give rise to the same birational contraction. But the base divisors we don't see. We don't see them from this birational contraction. So we also add them into the data. And when they are equal, we call them Mori equivalent. And now, a very easy consequence from the definition above is that each maximal cone of the Mori fan is of the following form, which is pullback of the Neff cone of X prime for some birational contraction X to X prime, plus the subcone spanned by exceptional effective divisors. So if you think that how do we get like when two line bundles are Mori equivalent, we see that they should give rise to the same contractions. So if we fix a contraction, we just take pullback of all the Neff divisors, and then we also include these exceptional divisors. Yeah, and it just follows from the definition. And now let me also introduce a notation which we denote by move fan. It's just the restriction of Mori fan to the so-called moving cone inside the effective cone, consisting of moving divisors, which means divisors without stable base components. And from the picture above, we see that the maximal cones of the moving fan are simply this part, only this part, because we don't have any exceptional divisors anymore. So it's an easier part, simpler part of this Mori fan. And also, we are not contracting anything. So in this case, it's just some small modification. We call it SQM because in all of the story, since we are working with singular varieties, and we know that not all Weil divisors are Cartier, so usually we need to put this technical condition of Q factorial. Yeah, but we can ignore this for the moment. So this is a simple part, like simpler part of the Mori fan, and the other cones of the Mori fan has this part generated by the effective divisors. Yeah, and they are called bogus cones. Okay, so this is just from some line bundles. We get another fan called Mori fan, and now one can prove that actually in the toric case, if YD is toric, then the Mori fan that we consider here, given by line bundles, is actually isomorphic to the secondary fan that we introduced in the beginning, secondary fan for the polytope. So yeah, so somehow here we can say that we already obtain a generalization of the secondary fan, because we can just take this Mori fan as a generalization. And however, considerations from mirror symmetry suggest us that we should do a further step, which is that we don't just want to take this Mori fan, but we would like to remove something from the fan. We would like to take a coarsening of the fan. And in the toric case, we don't do anything. So in the toric case, it just coincides with the secondary fan. But in general, we'd better not take this Mori fan, but we'd better remove something from Mori fan. And I'll explain why later why mirror symmetry is suggesting this. But now let me just say that so the idea is that we want to remove some pieces from the Mori fan, and here is where Berkovich geometry comes into the picture. So we would like to use Berkovich geometry to coarsen a little bit our Mori fan, and that will be our generalized secondary fan. And we will denote by sec of k. Yeah, so let me explain this. Yeah, so now let me explain what we do, the next step. So the first step is just we do this a little bit Mori theory, mainly just line bundles, sections of line bundles. And the next step, we would like to use non-Archimedean Berkovich geometry to coarsen a little bit, further modification to this Mori fan. Okay, so for this, we consider the universal torsor G over K, which is just the relative spec of a direct sum of line bundles. And we see that the restriction T, which is G restricted to V, is again log Calabial. And in order to bring non-Archimedean geometry into the picture, in order to use Berkovich geometry, now we just equip our base field. Yeah, I didn't say that what was our base field. It was just complex numbers. We were doing complex algebraic geometry. So now let's just equip our base field C with trivial non-Archimedean absolute value, which is just the norm of any non-zero element. The norm of 0 is 0, and the norm of any non-zero element is 1. So yeah, so now once we equip with the trivial non-Archimedean absolute value, we can take Berkovich analytifications. We obtain analytified T, analytified V. And what's really nice here is that here we are working with Calabial or log Calabial varieties. We have volume forms. And these volume forms give rise to canonical piecewise linear subsets inside these analytic varieties. We denote by SKT and SKV. So they are called essential skeletons, and they were proposed by Kontsevich-Sobelman and later generalized by Mustataniges, Temkin, and many other authors. So this is really like a unique feature of Berkovich spaces, that we have these piecewise linear skeletons. And in general, we know that these skeletons, they depend on choice of model and so on. But in the when we have volume form, we have a canonical the volume form also determines some canonical choice of this skeleton, and they are called essential skeletons. Okay, so we have these analytifications, and we had this map from T to V, and we get a map of essential skeletons between T and V. Now the claim is that actually we have a canonical section of this projection map from the essential skeleton of T to the essential skeleton of V. We have a canonical section phi. So I put in the parentheses that we need some extra care because we are not working really with projective varieties. So you know that if things are not projective, when we take the analytification, of course we have the analytification, but for things to work better, we'd better take this something smaller. I will say more about it. Anyway, the idea is just that when, in this case, we have a canonical section. Phi, I will explain the construction. It's very simple for non-Archimedean geometers. Yes. Okay. So then the idea is that, as I said, we are not content with this just the Mori fan. We would like to remove something out of the Mori fan. So what we do is that we will glue maximum cones of this moving part of the Mori fan, which is the simpler part, like we ignore all the exceptional divisors, base divisors, and so on. We glue the maximum cones of the moving part of the fan, for which this section phi coincide. And this induces a gluing of, so this, first of all, coarsens this simple part, the moving part of the Mori fan, and then it also induces a gluing, like a coarsening of the rest, and that is what our secondary fan will be. So this is the idea about how we use this phi. Okay, and now let me explain where comes this canonical section phi. So it's actually very simple if you think in terms of divisors and so on, but we can do it very generally since the audience are all experts of non-Archimedean geometry. So I can just do it in very general form. If we have x, curly y, formal schemes locally of finite presentation over K0, the ring of integers of some non-Archimedean field, and if we have some any f from curly x to curly y, flat surjective morphism with geometrically integral fibers, then of course we can take the generic fiber. We get f eta from x eta to y eta, and the claim is that actually there is a canonical section phi here. So what do we do? It's very simple. We just so we have our flat surjective morphism, curly x to curly y, and I want to construct a section of f eta. So for any y in the generic fiber, any small y in the generic fiber of curly y, we do the following. So we just want to specify where it goes in x eta. We do the following. We consider the complete residual field at y. And then at the level of these formal models, we take pullback. We just pull back this map from curly x to curly y along the map from this formal spectrum of the ring of integers of the complete residual field. So we get some formal scheme Z, and if we take its generic fiber, it's just the same as the fiber at Y of the generic fiber of X. Yeah, but here now this is a formal scheme over this ring, and we have a reduction map from the generic fiber of the formal scheme to the special fiber of the formal scheme. Since by our assumption, this guy is integral, so it has a unique generic point. And if we remember from Berkovich's theory that when we have a generic point, then the pre-image of the reduction map under the reduction map of this generic point, it's just one single point. It's just a unique point. And this is where the point Y should go under this canonical section. Yeah, so it's completely just, works just in general for all these formal schemes. But the idea is very simple, because eventually we are working with line bundles and divisors. So it's just like how we pull back the divisors. And let's see that when K has a trivial valuation, which is the context where we are in, and we have X, Y, K varieties, and we have some map F, flat surjective with geometrically integral fibers. So as I said that in order to be prudent in the case of non-projective varieties, we'd better not work with the analytification, but we'd better work with this bet symbol. I think, is it introduced in Tullier's paper or in other place?
Yes, in Tullier's paper on Stepanov's theorem, yes.
Yeah, in this case of K varieties, and it's also, if we think of it as a formal scheme, then it's just a generic fiber of the formal scheme. So it's a subset which consists of valuations whose center is inside this variety, and if it's proper, then the center is always inside, so they are equal. Yeah, so if we apply this generic fiber formalism, the generic fiber story before, we just get a canonical section in this case. In this case too. So it's a bit easier to state in this trivial valuation case, and this is the section that we take. Yeah, so now, as I said that we use this canonical section phi to glue cones of the Mori fan to obtain the secondary fan. And yeah, so the first thing that we checked is that if we glue, we actually get some convex cones because we cannot glue arbitrarily. And we can show that if we use this phi to glue cones, we actually get a convex cone. So with fixed phi, when we glue these cones, we get a convex cone. So this is for the moving part of the Mori fan, which is the simpler part. And the next, we show that actually it also induces a gluing outside this moving part. So for each maximal bogus cone, and outside the moving part, we have these exceptional divisors. and the cone is of the form, because outside this how do I explain? Outside this moving part, when we consider this birational contraction, it contracts a lot, no longer the same dimension. So when we pull back this part, it might not be the same dimension. So when we pull back this part, we also add to it the exceptional divisors. And it could be same dimension. It could also be lower dimension. So in this case, it's I'm sorry. So it's in this case we are considering birational contraction. Sorry about it. And yeah, it's the varieties K and Z, they are of the same dimension, but this Neff cone of Z has a smaller dimension. The Neff cone has a smaller dimension. So we have to add to it this exceptional divisors. And now, if we let this gamma B be the minimum cone of the moving part, maybe here I should write move fan. Yeah, it's a typo. So if we consider the minimum cone containing the minimum cone of the moving part containing the pullback of the Neff cone of Z, then if two maximum bogus cones have the same, so maybe it's difficult to read what is written here, but all I want to say is that now we already glued. So in our Mori fan, we have lots of cones, and we have a simpler like subfan consisting of moving divisors. Now we already glued many cones inside the moving part of this Mori fan, and all I want to say in the second statement is that like now we want to induce also a gluing outside this moving part. And if we look at the boundary of this nice moving part, so we have already glued. So the gluing of the moving part already induces some gluing on the boundary of this on the boundary of this moving part of the Mori fan. And now what we want to say is that this also induces a gluing outside of this moving cone. Because all I want to say is that if like on the boundary, two things are glued together, then they will have the same exceptional divisors. So if they are glued together, they will just induce a gluing outside of it. So it will not happen that we have like two bogus cones with different exceptional divisors, like things going in different directions. Then we are gluing them at the boundary of the moving part. This doesn't happen. The consequence of 1 plus 2 is that the gluing actually works, and the secondary fan we obtain is a rational polyhedral fan. Yeah, so so this is our generalization of the secondary fan to the beyond the toric varieties. And now it's also a more geometric construction with respect to the combinatorial construction in the toric case. Okay, If you have questions, please do not hesitate.
Do you want to give a hint why point 2 is correct? Why is it that you cannot glue two different bogus cones, as you call them, having the same boundary data?
Yeah, I mean, the proof was, it's actually a bit technical, and how about let's discuss it after the talk.
Sure, it's up to you.
For the proof of the second, part. I don't have an immediate, like, intuitive answer to your question here. Okay, so maybe let me say something about why we do this, why we introduce this secondary fan. So our motivation came from the study of moduli space of Calabial pairs. And in short, we want this secondary fan, or more precisely, the toric variety associated to the secondary fan to be some base, to be some moduli space of Calabial pairs. So to be some base over which we have these Calabial pairs. So it was motivated by the following conjecture, which itself came from considerations from mirror symmetry. We consider a moduli space of triples, X, E, theta, and these triples, they have been extensively studied in the literature. They are called polarized Calabial pairs. Here we have three things instead of pair, because let me first explain what are these things. So X is a connected smooth projective variety, and E is an anticanonical divisor, which is normal crossing with a zero stratum. So zero stratum just means that I have many divisors, many irreducible components intersecting until a point. And also we assume each piece is smooth. And furthermore, theta is an ample divisor not containing any zero stratum of E. So we consider such triples. They are called polarized Calabial pairs because XE is a Calabial pair. Since E is anticanonical, so this pair is Calabial pair, and theta is a polarization. So that's why it's called polarized Calabial pairs. And we are interested in the moduli space of such Calabial pairs. And motivated by mirror symmetry, it's very tempting to think that this moduli space, it's like almost a torus. So here we just say unirational, but we have a more precise form of the conjecture above, which actually suggests that it's almost a torus. But in order to state the conjecture, I just review some basic notions from birational geometry. Yeah, somehow we used some birational geometry a moment ago, but now it's a moment ago it's for this interpretation of the secondary fan in terms of line bundles and Mori theory. And now let me introduce some extra notions from birational geometry for the study of these moduli spaces. So as we know that in order to study, like to compactify moduli spaces, we need to take singular varieties into the picture.